HVAC engineers and designers. This is perhaps the most important concept if you want to graduate from a number cruncher to a full-fledged engineering consultant who actually understands how systems work. I'm going to break this into two parts, and the first part is going to be part one, space sensible heat ratio. We're talking about proper system sizing. The big question is, are you undersizing your coil? If you don't understand space sensible heat ratios, you probably are. All right, first let's set the stage for this example scenario. We've got a zone here, and we need to condition this to our target set point of 72 degrees at 50% relative humidity. Now, we've got a bunch of load in this space. We've got people, lights, we've got equipment, sensible loads, latent loads, we've got exterior load here. So the first thing we're gonna do is actually calculate this load, and let's pretend we've got 10 people in here. Boom, there we go. So you've done a load calc and it comes out like this. People load, sensible component comes out to say 2,500. Latent component comes out to 2,000. You've got equipment load right here. Say this pot of chili. Equipment and miscellaneous we'll say is 3,000 sensible from the stovetop and another 1,000 of latent from moisture. Lighting load, let's just add another 500 there. And then external load from the walls, windows, roof, we've got another 1,000. So these are the space loads. And if we add these up, sensible comes out to 7,000 and latent comes out to 3,000. Now, what is our sensible heat ratio? Our SHR is going to be equal to our sensible load over our total load being sensible plus latent. So in this case, we get 7,000 over 10,000. This gives us an SHR of 0.7. We're going to be plotting this on the psych chart, but for now, let's just put a pin in this. Okay, next, we're going to calculate the CFM required to condition this space. We'll start with 55 because that is pretty standard, but it's actually a big assumption and it might not be good enough. So if you just take 55 at face value and use that, you might be undersizing your coils. I'll explain in a moment. First, at 55, we're going to calculate our CFM. Our CFM is based on our space sensible load. Now, why is it based on space sensible load and not the space total load of 10,000? That is because the air that we are introducing to the space is only handling the sensible load. If we were handling the latent load, that would mean moisture is being extracted and that latent load is being extracted in the space, which is not good. We want to extract that moisture outside of the space so we don't have condensation problems, mold problems, etc. So that's where system design comes into play. We're going to be condensing moisture out of the air outside of the space so that we can drain that condensate properly. So this airflow is going to handle the sensible load, but we also want this airflow to be dry enough to absorb the moisture, not extract it, but absorb it. So here we go. I've reworked the sensible heat equation. CFM is equal to our space sensible load divided by 1.1 times delta T. The delta T is going to be the space set point of 72 minus the supply air temp of 55. This is going to give us a CFM of about 375. Now, this CFM is going to bring us to 72 degrees Fahrenheit. It is going to handle that space sensible load. But like I said, we need the air to be dry enough to absorb the moisture that's being added to the space by some of these latent loads like this here, or just all the occupants breathing out humid air. To do this, let's look at the psych chart. All right, setting the stage on the psych chart. Our set point is 72 degrees at 50%, which means we're going to be right about here, and then at 50% puts us right here. This is going to be our set point. Now, we're starting with 55 degrees supply air to the space as our assumption, which is going to be right here. Almost certainly it's going to be at the dew point line because based on your system setup, you're going to end up having some outside air intake. It's going to be mixing, and then you're going to have to cool that air, and it's going to be saturated. Now, that's going to come with part two. Part two, we're going to talk about the system sensible heat ratio and how we get this air to the supply state that we want. Right now, we're just going to be looking at this state and we're going to ask ourselves, is this the right state for supply air? To understand that, we need to understand the space sensible heat ratio. This can be plotted on the psych chart. Now remember, we put a pin in it. Our space sensible heat ratio is 0.7. This represents a slope. It represents a process. And to find this slope, we can look at a sensible heat compass. My psych chart has one. And we're going to find the 0.7 mark on this compass, which is right here between 0.8 and 0.6. Then we're going to draw a line from this point through the middle. It's going to look like that. And I'm making mine extra long. Now that we have this line, the important part about this line is the slope. This line can go anywhere on the psych chart. It's the slope that matters, and we're going to use this to start to analyze our system design, our coil design. I'm going to take this line and I'm going to plot it on my psych chart. I'm going to have it go straight through my set point, just like that. Now, what does this tell me? This tells me that the sensible heat gain and the latent heat gain in my space follows this slope. I introduce air into the space, but there are sensible gains, latent gains, and they are at this ratio right here. They're at this slope. That being the case, if I move this line such that it intersects with my supply temp of 55, this is what the actual process in this space looks like. I introduce 55-degree air. My sensible and latent gains in the space are actually going to bring it up to this point right here. We're looking at about 65% relative humidity. In other words, I cannot achieve 50% relative humidity with a supply state of 55 saturated. If I want to achieve 50% relative humidity, then my supply state needs to be somewhere along this slope. It could be here, it could be here, it could be here. As long as it's along this slope at the correct CFM, I will be able to achieve the moisture absorption that I need and actually maintain a 50% relative humidity in this space. So this 55, I mean, it's a good rule of thumb, but in my scenario with a 0.7 space sensible heat ratio, I'm just not going to be able to achieve it unless I do something else. So what are our options? Option 1, I can change my set point. Based on how this is set up, if we're sticking with 55 at that CFM, then instead of 72 at 50, I can achieve 75 at, let's say, 60%. In fact, I'm a little bit under. So if 75 at 60% is acceptable, and that is still within the ASHRAE 55 comfort range, then we can do that. The system will work just fine. And this is a really important conversation to have is, hey, if the owner is looking for 70 degrees, 50% dry, and you have budget limitations, you have unit limitations, then you can plot this out and show them not possible, but we can do 75 at 60% and still keep the same size unit and stay within budget, and that's a helpful conversation to have. However, if this original set point is a requirement, then option 2 is you can just drop your supply temp down to about 43 degrees off coil. This is not the best option. It does add a lot of coil load. Like instead of conditioning down to 55, you're actually going down and then some. And that's going to be a much larger coil, much larger unit. But beyond that, 43-degree air supplied into the space is not comfortable for occupants, and you have to reduce your airflow. Otherwise, you're going to short cycle. 43-degree air in is going to handle the space sensible load very quickly, which is again how we calculate our airflow. Basically, it's going to handle that dry bulb temperature set point very quick. It's going to shut the unit off, which means it's going to be short cycling. And if you don't have enough airflow, you're not introducing enough air to actually absorb moisture. In order to absorb moisture, you need full mixing. You need to give your air a chance to actually mix and absorb that moisture. So if you drop it this low, your airflow goes way down. It's really cold. So if anybody is right next to a diffuser, that's going to suck. And then you just aren't having the circulation you need to make sure you get full mixing, and that latent load that is present in the space actually gets absorbed and returned out or exhausted out. This is not the best option. It's possible, but your system performance is not going to be optimal, and you might still have the same humidity problems as before, again, because of airflow. So option 3, you can add reheat. Instead of your cooling coil stopping at 55 or going all the way down to 43, you can cool down to, say, about 47, and then you can add a little bit of reheat. So that's going to heat the air back up and is going to put your new supply state at about right here. So just about 55. In my case, it's a little bit more, but that does put you nicely on the space sensible heat ratio line. And at this state, you have warm enough air to be comfortable, but it's also dry enough to actually take care of the latent loads in the space, and you'll be able to have enough airflow to make sure you get full moisture and you actually give your system a chance to absorb that latent load. Too often, I see engineers just take 55 at face value. They don't actually take that extra step to understand what is going on with the psychrometrics specific to their project, their spaces, and is 55 the right number, or do you need to design your supply to actually handle your sensible and latent. So in some cases, this will work. In my example here, this does not work if I am indeed trying to maintain this set point. So I give you some options to resolve that. In part 2, I'm going to cover what happens in the system in order to achieve the set point that you want. We're going to talk about air mixing, outdoor air intakes, and what coil loads look like in the overall system configuration. That's going to be part 2, and we'll see you then.